Imagine a refrigerator with no conventional compressor and no tubes carrying circulating refrigerant, and none of that familiar humming sound you hear in the kitchen at night. Instead, inside it are magnets, metal plates, and a material that alternately heats up and cools down under the influence of a magnetic field. It sounds like a device from a science fiction story. But in Beijing, researchers from the Chinese Academy of Sciences have already created a fully solid-state magnetic cooling system. And the most interesting thing is not that it can produce cold. Magnetic cooling has been known for a long time. The real breakthrough lies in how scientists learn to transfer heat without using liquid. For decades, this single detail prevented magnetic refrigerators from leaving the laboratory. Stay until the end, because we are about to explore how a magnet can cool metal, why scientists removed liquid from the system, and why this technology may first appear not in your kitchen, but inside computers, electric vehicles, and data centers. To understand the scale of this idea, look at the technology around you: the refrigerator in your home, the air conditioner in your room, the climate control system in your car, the freezer in a store, and the equipment that keeps medicines cold all operate according to the same basic principle. A compressor compresses the refrigerant. As it is compressed, it heats up and releases heat outside. Then the pressure drops, the refrigerant expands, cools down, and absorbs heat from the space that needs to be cooled. This cycle repeats again and again. The technology is reliable and has long been a foundation of modern life. But it comes at a cost. The compressor consumes electricity, creates noise, contains moving parts, and wears out over time. And the system must contain a refrigerant. If some of these substances leak, they can affect the climate far more strongly than carbon dioxide. For example, the global warming potential of R134A refrigerant is estimated to be approximately 1,430 times higher than that of carbon dioxide. The problem becomes much larger when you consider how many cooling systems are operating across the planet. That is why engineers have long been searching for a way to move heat without a compressor and without gases that can leak. And this is where magnets come in. Some materials exhibit the magnetocaloric effect. When a magnetic field is applied to such a material, its internal magnetic state becomes more ordered and its temperature rises. When the field is removed, the material cools down. It is easier to understand this using a rubber band as an example. If you quickly stretch a rubber band and press it against your lip, it will feel warm. When it returns to its original state, you can feel a slight cooling effect. Nothing inside the magnetic material is physically stretched by hand, but repeatedly switching the magnetic field on and off produces a similar change in temperature. This effect alone does not create a refrigerator. It only provides a material that can be alternately heated and cooled. The main challenge is to remove heat from it at exactly the right moment, transfer that heat to the hot side of the system, and then return the cooled material to the cold side. And this is where older designs encountered a limitation. To transfer heat through the magnetic material, liquid was usually pumped through it. But liquid moves relatively slowly, creates resistance, and requires channels, pumps, and seals. It limits the operating frequency of the cycles and therefore the amount of heat the device can transfer within a given period of time. In other words, the magnetic material could operate faster, but the liquid could not keep up with it. In 2024, a team from the Institute of Physics of the Chinese Academy of Sciences proposed a different approach. What if liquid were removed entirely and heat were transferred directly between solid plates? The researchers created a hybrid magnetic regenerator. In this system, a layer of magnetocaloric material is placed next to a layer of highly thermally conductive material. These layers move relative to one another and make contact in such a way that heat passes directly from one solid material to another. When the magnetic field causes the magnetic material to heat up, the heat moves into the neighboring thermally conductive plate. When the field is removed and the material cools down, the cycle continues in another section of the device. A sequence of these contacts gradually transfers heat from the cold side to the hot side. There is no liquid that needs to be pumped through narrow channels. There are no pressure losses and no unused volume inside tubes. Most importantly, the previous limitation on operating frequency disappears. In their theoretical 2024 design, the researchers demonstrated the possibility of operating at a higher frequency and achieving a significantly greater specific cooling capacity than most previous liquid-based magnetic systems. But the story did not end there. In 2026, the same research group presented a physically assembled compact device designed to cool electronics. It used gadolinium plates, highly thermally conductive solid components, and small servo motors that moved the layers relative to one another. So this is not a completely motionless refrigerator. The prototype does contain mechanical movement, but it has no compressor and no circulating liquid refrigerant. This is an important distinction because the popular description, "no moving parts," sounds impressive, but it does not yet fully match the actual design. Tests showed that, at comparable input power, the compact system achieved a heat transfer coefficient approximately 3.5 times higher than that of the small fan selected by the researchers for comparison. This is exactly why the technology's first major application may not be a household refrigerator. Modern processors, electric vehicle batteries, and server systems generate large amounts of heat within very small areas. A fan cools a relatively large area, while liquid cooling requires channels, pumps, and sealed connections. A solid-state magnetic cooling system could potentially be positioned directly next to the point where overheating occurs. This creates not simply a new type of refrigerator, but a tool for precise thermal management. And now I have a question for you. What would matter more when choosing a next-generation refrigerator? Or the absence of compressor noise and refrigerant, or the familiar low price? Write your answer in the comments. And if you enjoy exploring technologies that could transform the most ordinary objects around us, support the video with a like and subscribe to the channel. But before declaring the compressor obsolete, we need to discuss the main limitation. This is not yet a finished household refrigerator. The 2024 study described a conceptual design, while the 2026 device was intended primarily for the localized removal of heat from electronics. Scientists still need to prove that a similar system can cool the large internal volume of an ordinary refrigerator affordably, reliably, and continuously for many years. There are other challenges as well. Magnetocaloric materials and powerful permanent magnets can be expensive. Some existing designs use gadolinium and other specialized materials. The power must be increased, the cost reduced, durability verified after thousands and millions of cycles, and all the components integrated into a single efficient system. At the level of an individual material, the technology looks promising, but between an effect demonstrated in a laboratory and a refrigerator that can be purchased in a store lies an enormous amount of engineering work. And yet, an important change has taken place. For decades, magnetic cooling encountered the same barrier. The liquid responsible for transferring heat slowed down the entire process. Now researchers have demonstrated a different path, transferring heat directly between solid materials. Perhaps this is exactly how major technological changes begin. Not with a finished appliance displayed in a store, and not with a dramatic announcement of a revolution, but with a single detail that engineers have finally learned to approach differently. The refrigerator in your kitchen will not disappear tomorrow, but its compressor is no longer the only possible way to produce cold. And now one question remains. Which familiar machine will be the next to lose a component without which we cannot imagine it operating today?